All right, should be good. So the question is, why was this worth a Nobel Prize for palladium catalyzed coupling reactions? And these fall into the category of organometallic reactions. So if you want to learn more about this, Chem 470 inorganic chemistry covers a lot of this stuff. The reason why these palladium catalyzed coupling reactions are so important is they're carbon-carbon bond forming reactions, and you don't know very many of those yet. So you can build up complex structures from simple structures, and in particular they couple sp2 and sp hybridized carbons. And those are typically not available by nucleophilic alkyl substitution, right? Because they're not sp3 hybrid. So if you're talking about an alkenyl halide, right, something that's got a bromine or a chlorine or an iodine or whatever, you can't do either SN2 or SN1 reactions at the sp2 hybridized carbon because the carbocation is not stable, and there's no kind of backside attack possible when you have that pi bond in place. So the complexity is kind of misleading. It's fairly straightforward. You're talking about something that has a bromide, right? Either an alkenyl bromide or an aromatic bromide, an aryl bromide. So we'll just put an R group on the benzene, and it can be iodide as well. Less commonly chloride, mostly bromine and iodide. So this is what we call an aryl bromide. The term aryl just refers to a substituted benzene, right? And again, sp2 hybrid, so you can't do any coupling reactions. And then on the other side, right, we'll have either just a plain old alkene, or in some cases an alkyne, or some other derivatives of these substances that have like a metal on there. So one of the coupling reactions has trialkyl tin attached to your carbon-carbon double bond. And when you see the tin, that's the Stille reaction, named for Clark Stille. He wasn't one of the ones that shared the Nobel Prize. The problem with the tin is it's very toxic, so these trialkyl tin reagents are not particularly, something you really want to work with. And then also you can get coupling reactions with a boronic acid in place of the hydrogen of the alkene or alkyne. So we could make a diaryl where we take out the boron and the bromine and we connect two benzene rings together. Being able to connect two aromatic compounds together like that, right? So this aryl boronic acid, when you see that, that's the Suzuki coupling. And when you see the alkyne, that's the Sonogashira reaction. So all these guys, Suzuki, Stille, Sonogashira, and Heck, who was one of the original people, involve a different reagent kind of on the right-hand side, but they're all working with either an alkyl or an aryl bromide, or in the case of the Suzuki reaction, you can actually do it on plain old alkyls, which doesn't really work in the other cases. The Stille and the Sonogashira reactions don't really work for alkyl bromides, only aryl and alkenyl bromides. So it's a coupling reaction between either two sp2, or an sp2 and an sp3, or an sp and an sp2 hybridized carbon. They all involve palladium. Or nickel, and you know that the periodic table, that's the nickel palladium platinum triad, right? So nickel complexes and palladium complexes share some commonality, And you've seen that because the catalytic hydrogenation also involves molecules, or atoms rather, from this same triad. So nickel, palladium, platinum, they all involve ligands, including atoms from the nitrogen, the pnictogens, which is the nitrogen, phosphorus, arsenic, antimony. And generally it's the phosphorus and arsenic derivatives, so triphenylphosphine, for example, or triphenylarsine, are common ligands, and most of them involve a base, and usually an amine base, to quench the acid that gets liberated. So you'll often see like triethylamine in these reactions. And the triethylamine, right, because when you couple this together, the hydrogen and the bromine are going to come off and you're going to liberate HBr. Right, same here, the HBr would be liberated, and you need some base that's going to quench that. They're much less sensitive to traces of moisture or oxygen than are the Grignard additions. The Negishi is the third guy that shared the prize. Negishi has a zinc in place of the tin or the boron, right? So it's a different metal that's doing the coupling. And then there's another Kamada reaction that involves like a sodium or a potassium. So they involve some kind of metal attached to a carbon bond. The source of the palladium is often palladium acetate or chloride. These are palladium-2 species. Palladium-2 salts, but the reactive palladium is palladium-0 in the zero oxidation state. So these palladium salts are converted to a palladium-0 species before the reaction. And you can actually buy palladium-0 species. It's quite common, actually. You can buy what we call tetrakis, which is a square planar, tetrahedral. So this is tetrakis, triphenylphosphine palladium. Palladium-0, where you've got 4 of these triphenylphosphine ligands attached to the palladium. And that's in equilibrium with species that contain fewer ligands. And this is the one that really matters. It's a divalent phosphorus with 2 triphenylphosphine ligands, so it has room in its coordination shell to add something else. Palladium-0 is a D10. Species. And you may remember from last semester in General Chemistry 2 that D10 species tend to like linear or octahedral complexes, whereas palladium-2 is a D8 species. And you may remember that D8 likes to be square planar because it can keep the x squared minus y squared, the dx squared minus y squared orbital empty, and that high energy orbital being empty allows the whole thing to be stabilized. So this tetrakis triphenylphosphine is generated in situ by reacting palladium acetate with 5 triphenylphosphines, and what you get out is this tetrakiss and triphenylphosphine oxide in the presence of water. Okay. It's a yellow solid. It's not very stable. You have to keep it under argon, but it's stable compared to a lot of other species, so you can buy it. And there's lots of variation in the ligands, but they all share the commonality of having palladium with a couple of ligands attached to it. And that's where the reaction is going to start. And that's going to start pretty much the same for any of the cross-coupling reactions. So what's going to happen is the palladium with these, and I'm just going to use triphenylphosphine, but understand that these phenyl groups could be something else, these phosphorus could be arsenic, and it really won't affect anything. The important thing is that it's palladium 0, and it's got some pnictogen ligands attached to it. Clear so far? Am I making any sense? The coordination chemistry is something you may have forgotten a little bit. The first step is always what we call an oxidative bond insertion. So what's going to happen is whatever your alkenyl or alkyl halide, the palladium is going to insert itself in between the carbon and the bromine. And it will initially do that so that you have the alkenyl group and the bromine in the cis isomer, but that cis isomer rapidly isomerizes to trans, and the trans is more stable because the bulky ligands can be on opposite sides of each other. So then it will really look like it just inserted itself into the bond. And now you've got a carbon-palladium bond. And this is palladium in the 2 oxidation state. So when we say it's an oxidative bond insertion, we're changing from palladium 0 to palladium 2. And we'll change back to palladium 0 because this is catalytic, and you only really need about 1 mole % of palladium, which is good because palladium is incredibly expensive. Right, so we've got this carbon-palladium bond with our ligands, 2 ligands. Oops, I just rotated it around. I didn't mean to do that, but whatever. And the next thing for the Heck reaction, anyway, will be for the pi bond of the other species to complex to the palladium. So it's a pi bond that's donating into the palladium. So you've got really kind of a 6-coordinate palladium, but it's through the pi bond, not through the sigma bond. All right, so step 2 can be considered to be this isomerization after the oxidative bond insertion. And then step 3 is pi complex formation. And step 4 is a bond migration, which is basically analogous to an alkyl shift. What's going to happen is the alkyl group's going to shift off the palladium onto the less substituted end of the pi bond, and then this pi bond is going to form a sigma bond to the palladium. So we've actually just changed the structure here. We've changed what's attached to the palladium. still got the two diphenylphosphine ligands and the bromine. Oops, that's not there, that's here. Right. And initially this is trans, and then we do another isomerization. And in many cases, this is the rate determining step. Where this and the bromine are going to end up on the same side, and our two ligands are going to end up cis to each other again. Okay. So we got our bromine, and then we've got our and then the pi bond. And the last step of the Heck reaction is an E2 elimination. So what we're going to do is we're going to take the base, and this is a reductive elimination process. So we're going to go back from palladium 2, right? It has been palladium 2 throughout this process. And it will become palladium 0 again. We're going to do an E2 elimination where we take off one of these hydrogens with our base and boot out the palladium, and the bromine falls off. So we regenerate the catalyst and we reform the pi bond. So we've got the original pi bond, right, from the species, and we've just remade this other pi bond. And we've generated our palladium 0 species again. And the bromide ion, which is complex to our BH+, right? So we basically just quenched the hydrogen bromide. So the catalyst is regenerated. And the new bond is between the two alkenes. Right? So it's actually very easy to write the product of a Heck reaction. Right? If you've got an alkene, let's just say we had an alkenyl bromide that looks like this, and we're reacting it with another alkene. All you have to do to draw the product is to pull out HBr and connect the CC bond. So you might see a reaction that said 1% palladium acetate in the presence of triphenylphosphine and triethylamine at 100 degrees C, right, something like that. And then your product simply takes the HBr out and forms the new bond. And you'll notice that the stereochemical relationship here, right, it's the trans, it's E selective, and it's retention of stereochemistry on this part. So if all you have to do is write the reaction, you basically just need to recognize it as a Heck reaction. When you see the triphenylphosphine ligand and the palladium acetate in a low mole percent like that, and your starting materials are alkenyl bromide and another alkene, it's a Heck reaction. And then remove the HBr and couple it. If you're not asked for the mechanism, it's not that difficult to come up with the product. The mechanism is complicated. The mechanism of any transition metal catalyzed reaction is always complicated, kind of messy. Did I make sense? Were you able to follow at least a little bit? Oxidative bond insertion followed by isomerization, then a pi complex, then a bond migration, and then a reductive E2 elimination. So it's not a huge number of steps, but the molecules are big and complicated, which makes it a little bit difficult to write the whole mechanism out. So there's one video that covers the Heck reaction, and there's another video that covers what we call the cross-coupling reactions, which are the other. And they involve a transmetallation step. And that transmetallation step is involved instead of pi complexation and bond migration. So in a way they're a little simpler than the Heck reaction. For the Sonogashira reaction, for example, you still have that same palladium species. So let's say we started with like a methoxy bromobenzene, and we're going to react this with our tetrakis palladium. We're still going to do the oxidative bond insertion. And we're still going to do the isomerization. So that what we end up with when we're done is basically the same thing that we had for the Heck reaction, where we now have a palladium 0 species with the aromatic ring attached and the bromine and the two triphenylphosphines opposite each other. And this is now going to react with an actual copper reagent. So the Sonogashira reaction also has a cuprous salt, a copper 1 salt, often copper 1 iodide, cuprous iodide. And the cuprous iodide reacts with the alkyne to form an alkynyl copper species. So you actually have copper connected directly to the alkyne, whatever the R group is on the alkyne, and the base here, the triethylamine, will have taken away the hydrogen from the alkyne, and obviously the iodide is going to be liberated. So you actually make a copper complex. Right. So in that respect, it's similar to the Stille or the Suzuki reaction, in that you've got one species attached to one metal and one species attached to a different metal. And what's going to happen is they're just going to switch partners. So we've got this, and we've got our copper with the alkyne on it. And this is going to migrate from copper to palladium, and the bromide is going to go with the copper. So there's a transmetallation. And then the aromatic is still there, plus CuBr, which is again cuprous bromide, and so it's catalytic in copper as well. And then we have to do the cis-trans isomerization again, because the last step of the reaction can't occur until these two things are cis to each other. And again, that's probably the rate determining step. And we do a reductive elimination where this basically migrates over to form the new carbon-carbon bond and returns the electrons to palladium. To regenerate the palladium catalyst. Now palladium 0 again, and form the new bond. There aren't many reactions that form new carbon-carbon bonds like this from an alkyne to an sp2 hybridized carbon. You can make the alkynyl anion and do a lot of SN2 reactions of the alkynyl anion attacking an sp3 hybridized carbon, but to attack an sp2 hybridized carbon is relatively unusual.